this is homework 2, part C. So to begin, I will derive the equation for our thermal resistance for our pipe that we used in our previous video with some insulation around it. So to do that, we'll start with our thermal resistance that we derived for the pipe, which we said is equal to the natural log of the outside radius over the inside radius divided by our thermal conductivity times 2 pi L. So in order to get our total thermal conductivity, thermal resistance, we'll need to add our conductive thermal resistance to our convective thermal resistance. So to find our convective thermal resistance, if we use our formula for heat flow by convection, which we know is our coefficient of convection, H times area multiplied by our change in temperature, we can use that. Since we know, we could say our change in temperature is equal to our heat flow times thermal resistance. If we divide this equation by our change in temperature, we could say that our thermal resistance for our convection is equal to 1 over HA. And our area in this case will be 2 pi R L. So 2 pi times our radius times our length. So writing that in, that's what we'll get for our equation for our thermal resistance. So if we combine these, say our total thermal resistance is equal to natural log of our outside radius over our inside radius divided by our thermal conductivity times 2 pi L plus 1 over our coefficient of convection times 2 pi R L. So in order to determine the optimized radius for our insulation, we'll need to take the zero of the first derivative of this equation. So what that'll look like is, say, say R1 over R2 times 1 over R1 divided by K 2 pi L plus 1 over our 2 pi R squared L, and also this will be negative. And all this will be equal to 0. So rewriting this, we'll say inside radius over our outside radius times 1 over, see these cancel, thermal conductivity times 2 pi L is equal to 1 over 2 pi L. So if we factor out our 2 pi L we'll cancel these. And we'll be left with 1 over our outside radius divided by thermal conductivity is equal to 1 over heat transfer coefficient times our outside radius squared. So we can rewrite this as 1 over KR2 is equal to 1 over which will simplify down to our radius equal to thermal conductivity over coefficient of convection. So with that, we can then, so that's our value for our 0. So now we need to determine if it's a minimum or a maximum. In order to do that, we will need to find the second derivative. So we'll say second derivative, our total, for that we'll get the following. So if we plug in our value for R2, or our outside radius there, we'll get get 2 over h, no, 2 over 2h squared over our thermal conductivity minus 1 over, or say h squared over our thermal conductivity cubed. So we can clearly see that this first value will be larger than the second value, meaning we'll have a positive number. And because it's positive, we will be concave up, meaning we'll have a minimum. So what this will look like graphically will be something like this, where our origin will be our radius without any insulation at all, and here our minimum value here will be this R2 value. So our thermal conductivity over our coefficient of convection. So anything below our x-axis here will have greater heat transfer than just having the pipe without any insulation. And the reason this happens is because the heat transfer from convection will be greater than the resistance given by the insulation.